Hello, everyone. It's nice to be with you, and I hope at the end of this meeting you will feel comfortable with our message. Let me introduce myself. My name is Peter Livingston, and I am an inventor, granted over 40 patents during my 32 years as an applied physicist in the aerospace industry. I am also the founder of the Alembic Group Corporation. I've given this presentation a few times before, so I will answer 3 questions during its course. The first is, what is the problem? The second is, what is a gamma ray? And the third is, how is the first problem partially solved by the second? Here's the problem. Coal-fired power plants are a major source of atmospheric carbon dioxide. According to a recent estimate, 40 billion tons of carbon dioxide are dumped into the atmosphere every year from power plants and other sources. The current approach resolving the problem is conventional, costly, and environmentally questionable. It is called carbon capture and storage, CCS, or carbon capture and sequestration, if you prefer. It works by capturing waste carbon dioxide from large point sources such as fossil fuel plants, liquefying it, transporting it to a storage site, then pumping it underground. There is an alternative. Process the carbon dioxide into other useful chemicals that are the basis for a range of products, from plastics to denture cleaner. That alternative is a brand new chemical industry, and that is the answer to the third question. This picture is the expected result from not solving the global warming problem. New York and many other coastal cities, including most of Florida, will be inundated by rising sea levels. Gamma radiation is the power behind this revolution. It is energetic, abundant, and essentially free. This means that chemical transformation of carbon dioxide does not depend on the power grid and, incidentally, uses no reaction promoters or catalysts. We're not the first to suggest the importance of this resource for transforming carbon dioxide. It was featured in a book entitled Greenhouse Gas Carbon Dioxide Mitigation, Science and Technology, and it was published in 1998. Our grand business scheme depends on these 4 points. The first is to define the revolutionary new chemical industry by creating a practical plant for carbon dioxide transformation by means of nuclear radiation. The second is to build and install small, semi-portable plants adjacent to nuclear power plant cooling ponds. At present, there are about 507 nuclear power plants in the world, and each must have a cooling pond to store fuel rod assemblies until they're safe to reprocess or move to a site. The third point emphasizes that spent fuel assembly transport has not yet been permitted in this country, but when it is, we will design, construct, and sell much larger plants using these assemblies at any place, no longer tied to a nuclear power plant. The fourth point is a logical extension of the first 3. If the others are making money with this chemical process, why not us as well? The banner sums it up. There is a general chemical equation at the bottom showing what happens to carbon dioxide. The word titrant here stands for a bunch of different chemicals. The specific product or products generated depends on which titrant chemical is used. Notice the picture on the lower right. This is an actual picture of the Fukushima spent fuel rod cooling pond glowing in the blue light created by nuclear radiation. We see it, and it is safe, because the actual assemblies are about 25 feet underwater. That amount is an adequate radiation shield. We bring our chemicals to the radiation underwater and never need to disturb any assemblies. Our special reaction vessel is designed to fit in an empty fuel assembly location. Here we build the small chemical plant adjacent to a nuclear power plant cooling pond in 10 steps. We start with our specially designed reaction vessel. It is inserted 25 feet underwater in a cooling pond. Next, we introduce a spent fuel rod assembly that is an intense source of gamma rays. The chemical path starts with a Dewar storage tank of carbon dioxide. Then we add a second chemical titrant Dewar tank. It could contain hydrogen, methane, or any one of a number of titrant chemicals chosen to produce a particular chemical product. Then we warm the stored liquids to room temperature, mix and pressurize them as needed in a box called the mixer. Then we pipe the gas mixture down to the reaction vessel. We flow the reactant gases into the reaction vessel and the products flow out. Typical dwell times are measured in seconds. We pipe the products to a product separator to separate wastewater from the product. And lastly, we liquefy the desired product or products and store in the product Dewar tank. Before showing you the money to be made, I want to show you the variety of chemicals that can be made this way and what their uses are. Our plant synthesizes the gases in the left-hand column and the products in the right. In many cases, there are intermediate chemical stages leading to this amazing list of applications. You'll agree that is quite a few. But this is not the end. There are others to be made as well as gotten by tinkering with the carbon dioxide mixture involving other reactants. Our extensive modeling for these and other chemicals shows that chemical transformation from reactants to products occurs rapidly. All of these chemicals are produced in less than a minute, flowing through our special reaction vessel placed close to a fuel rod. This rapidity ensures a high volume output and ultimately a high profit margin. Here's a profile of 5 of our chemical outputs. From left to right, carbon monoxide, methanol, butyraldehyde, acrolein, and acetone. Here, we display daily production tonnage in blue, world price per ton yellow, and gross daily profit in green. The vertical scale is logarithmic in order to display all of the data. For prices and profits, the scale reads in thousands. For weights, the scale reads in tons. It is clear that butyraldehyde, that's the normal isomer, is the winner, probably from its use in the perfume industry. Acetone is in second place with a great variety of uses from solvent to chemical component. The takeaway message from this chart is that our process is a serious chemical feedstock industrial competitor with serious production rates and serious profits. Radiation safety is a paramount issue. There is no doubt about it. But let's consider the odds. There are 507 nuclear power plants worldwide, give or take a couple. Let's say they've been online for an average of 35 years. 40 to 50 years ago, there was a nuclear power plant building boom followed by a distinct loss of enthusiasm for nuclear power. There have been 3 major nuclear accidents since then, 2 of which were traceable to operator error, Chernobyl and 3 Mile Island, and 1 from a natural disaster, Fukushima. Take the latter into our account. Therefore, the odds are 1 in 17,745, expressed in reactor years, or about 0.005%. According to the National Weather Service, your odds of being struck by lightning during your lifetime, 80 years, is larger, about 0.008%. The important point here is that A, we bring our reactants to the fuel rod radiation field underwater, not the other way around, and B, our reaction vessel has a patented optical means for detecting any vessel size changes that might suggest a failure. But, like any risky business, such as working on live high-tension electrical lines, safety comes from rigidly following operating protocols, and it will be the case with our operation as well. Of course, this is a new venture, and some, invested in other technologies, will oppose it. The second bullet on the chart lists some examples of channel thinking. A basic fact, most or all of the primary feedstocks we talk about are derived from various chemical means, from petrochemicals or from coal itself. That means that the competition we must beat is the petrochemical industry, such as ExxonMobil. Others are old established players in the chemical feedstock and chemical utilization business. The second bullet addresses secondary players. These are technologies that are not now competitive with established processing. In fact, they have yet to enter the commercial market and must be considered under reconstruction. There are several important takeaways from this slide. The first is that we are in a position to disrupt, an economic term, old established industries because we bring a revolutionary technology to bear. A contemporary example, the loss of the photographic film industry to digital photography. We base this argument on three things we do better, right out of the box. First, our chemicals are not contaminated with petrochemicals and are absolutely pure. Secondly, the energy needed for carbon dioxide reduction with various reactants is derived from the radiation field, not from the power grid. Third, we do not need catalysts, and therefore we do not bear the expense of their acquisition and use. These three reasons guarantee our feedstock chemicals will cost less than those same chemicals produced by conventional means. The bar graph says it all. Based on the same 5 chemicals we profiled earlier, the payback times are fantastically short. Why is this so? Clearly, the combination of high output and world market price is very important. But the other reason is that our basic single reaction vessel assembly is cheap by manufacturing plant standards. One of the dominant elements is the plant form factor that requires our plants to be small and semi-portable. This enables transportation, a rapid setup of our plants, and also ensures minimum cost. Carbon engineering. Noun. Definition. A new technology consisting of carbon dioxide extraction and carbon dioxide sequestration processes. The former is any of several chemical-based schemes, and the latter are schemes based on radiochemistry, conventional catalyst chemistry, and biochemistry. To me, this is the most exciting slide of all. Here we are at the very beginning of a new journey to help rescue the planet from climate catastrophe, also to make money. To begin with, we are not alone. There are at least 3 startups competing with each other to find the most cost-efficient process for capturing carbon dioxide, not only at its source, flue gas, but also from the atmosphere itself. These groups are not our competitors, but our partners, because we offer a stable market for their captured carbon dioxide. At present, they view the petroleum industry as a customer, selling their captured gas to it at an unrealistic $100 a ton. The petroleum industry wants to use that gas in further oil extraction by injecting it into wells. Some would say this resembles fracking. Needless to say, our custom has far less ecological implications and, as mentioned earlier, is stable. Our technology partners have already attracted investments amounting to millions of dollars from wealthy individuals and funds and have been set up and running for several years. These data are drawn from our detailed business plan. The total is $14 million with a development time of 10 years. While the first milestone is fairly easy to predict, the uncertainty grows after that, since much depends on the pilot plant outcome. Estimates are that the cost of building a little plant is between $5 and $7 million. Therefore, the profit per unit is between $3 and $5 million. Thus, the sale of 3 single-vessel units would pay back the investors. Potentially, every nuclear power plant in the world, 507, is a candidate for our technology. That is a potential $5 billion in sales. This number does not include non-adjacent sites that will be built after the rod assembly transport problem is solved. Sales to power plants are ultimately self-limiting, but only the marketplace will limit the development of non-adjacent plants. We need to attract 2 kinds of investors: investment bankers, funds, and so forth, and cooperating nuclear power company owners that will join with us in the pilot plant demonstration. The main point: placing a monetary value on spent fuel rod nuclear radiation will have a profound effect on the spread of this new technology. The second point: an enormous effort must be made if catastrophic global warming is to be avoided. We form part of the solution. But invention doesn't stop here. Radiation chemistry opens the door to new products such as combinations of carbon with silicon and boron in compounds that may have application in the semiconductor world. It might even be possible to adapt our method to the capture of carbon dioxide itself, thereby avoiding the power consumption price tag. If that were to happen, carbon capture becomes much more attractive. Here is a brief look at my background. I benefit from both being well-grounded in chemistry and applied physics, and I bring this expertise to our invention. This picture was taken from the web and is vivid in my memory. I'm standing somewhere on the right in fatigues. My Air Force Military Operations Specialty, MOS, was that for Nuclear Effects Officer, and I fielded a team of technicians of a dozen or so to measure the electromagnetic pulse generated by a nuclear blast. We ultimately were successful, and we verified the correlation between a theoretical model and measurements. This information was used to protect the Cheyenne Mountain NORAD site. Needless to say, this was my first exposure to gamma rays on a truly industrial scale. Thanks for listening and watching. Let us, you and I, go out and change the future together.